There's a danger in probability. We saw in the last video what it means for two events to be independent of each other. And when this happens, it can make the math involved so much nicer to deal with. So the danger is that anyone working with probability has this incentive to assume that things are independent, even when they might not be. Here, I want to tell you about something called the binomial distribution, and it rests on a certain independence assumption. And it's one thing to say, if the assumption's wrong, the distribution doesn't apply. But I think we can get a little more sophisticated than that. Given that this distribution, and a lot of others deriving from it, are used all over the place, even when the underlying assumption might be questionable, a major goal here is for you to get a feel for the specific way that the distribution will be wrong if it's misapplied. As a central example, imagine that you're taking a quiz, and for now let's say it only has 3 questions on it. You want to place some probabilities on the 4 possible scores that you might get. That is, you want a distribution over the possible scores. You figure you know about 80% of the material, so on average, all else held equal, the probability of answering a single question correctly is 80%. Now if you break down what happens question by question, there are 2 possibilities for that first question, either you get it right or you get it wrong. Likewise, there's always 2 possibilities for that second question, right or wrong, and same goes for that third question. And what this leaves us with is 8 possible patterns for your performance on the quiz. Only one of these corresponds with a score of 0, wrong, wrong, wrong. 3 of these guys correspond with a score of 1, wrong, wrong, right, wrong, and right, wrong, wrong. Likewise, 3 of them correspond with a score of 2. And only one pattern gives a perfect score, right, right, right. For those of you who remember the counting methods that we talked about in the first video, this 1-3-3-1 pattern might make your brain start tingling with thoughts of binomial patterns and Pascal's triangle. But before immediately jumping into the counting methods that simplify and generalize this question, let's dig into how this situation is actually a little more complicated than it might initially seem. Take a look at one of those 8 events, like right, right, wrong, and think through its probability. It's very tempting, to say that this equals the probability of being right on one question, which we're assuming is 0.8, multiplied by another 0.8 for the probability of being right a second time, times 0.2, the probability of being wrong on a given question. However, we have said nothing so far about whether or not succeeding on one question correlates with success on another. To be concrete, imagine 1,000 different possible quizzes, where for 800 of them, you get the first question right, and for 200 of them, you get the first question wrong. Now consider your success with the second question. If your chances with each question were truly unrelated, then among the 800 quizzes where you got that first question right, you should get the second one right about 80% of the time, which would be 640 of those quizzes. But realistically, questions on quizzes are usually related. Maybe they build on each other, or maybe they circle around a similar subtopic. So among those 800 quizzes where you got the first one right, it might be more like, 740 where you get that second question right. I mean, more of those quizzes are going to be focused on ideas that you're comfortable with. Speaking more in the lingo, the probability of getting the second right conditioned on the event that you get the first one right is likely greater than 0.8. Likewise, looking at those 200 where you got the first question wrong, even though 80% of that would be 160, if there's some relation between questions, these are more likely to be the quizzes which, as a whole, cover ideas that you don't know so well. So it might be more like 60 of those where you actually get the second one right. Notice, and this is important, among all of the 1,000 quizzes, the way I've set up these numbers, it's still true that the total number of quizzes where you get the second question right is 800 out of the 1,000. So it's still true that the total probability of getting the second question right is 80%. It's just that those 800 are not divvied up proportionally along the split for the first question. That is, they're not independent events. And of course, this gets even more complicated when you bring in that third question. Each of those 4 outcomes for the first 2 might have their own miniature distributions for your success on the third question, with a disproportionate number of quizzes where you succeed on the third lying in the regions where you were successful on the first 2. The more accurate way to expand the probability of right, right, wrong as a product looks like this. the probability of being right on the first question, which we're assuming is 0.8, times the probability of getting the second right given that the first was correct, which, if there's correlation, might be greater than 0.8. And then that subspace is divided even further by whether the third question is right or wrong. So you have to finally multiply by the probability of getting the third one wrong, given that we're in that subspace, that you get the first two correct. This is more or less a reiteration of the point I made last video, that when you break up a joint probability into a product, you have to be sure to use conditionals. But the implication for the original question it's horrifying. Each of those 8 patterns of wrongs and right have their own expressions. And how are we supposed to give a reasonable estimate for every one of those conditionals? You probably just don't have the data to put numbers on those. So you can see how tempting it would be to set aside the caution that this problem deserves and just see what would happen if you do assume independence, that your success on one question is uncorrelated with your success on another. That would mean that the probability of getting any particular question right is always 0.8, no matter the results of the other questions. So a pattern like right, right, wrong has a probability of 0.8 times 0.8 times 0.2. Now what's nice about this is because order of multiplication doesn't matter, all 3 of the events with a single wrong have the same probability. It has 2 factors of a 0.8 and 1 factor of a 0.2. So the total probability of getting a 2 out of 3 on the quiz is 3 times 0.8 squared times 0.2, which happens to work out as 0.384. Likewise, all 3 of the events where you get exactly 1 correct have a probability 0.8 times 0.2 squared. So the total probability of getting a 1 out of 3 is 3 times that value, which comes out to 0.096. The one way to get a 0 has a probability of 0.2 cubed, or 0.008, and the one way to get a perfect score has a probability 0.8 cubed, 0.512. Rather than swimming in numbers, it's a little nicer to view these values in bar chart form. One way to think of this is to take the 1331 pattern for counting how many patterns of rights and wrongs correspond to each score, and then give a little extra weight to the scores that involve more correct answers, since with your 0.8 chances, those are more likely. If your chances for each question were 50-50, then the probability of each pattern of wrongs and rights would be 0.5 cubed. So the distribution would just be entirely determined by this 1331 pattern. If your chances were more like 65% for each question, things would be skewed a bit to the right, but not as much as they are for 80%. And this is all well and good, and the math is pretty, but again, it's almost certainly wrong. The true distribution should give more weight to the scores of 0 and 3, and less to the scores of 1 and 2. This is one of those facts that's maybe better understood through emotion than logic. Imagine you go into the quiz knowing 65% of the material, and then you end up with a 0 on the quiz, and just how unfair that would feel. Sure, you didn't know everything, but 0 out of 3 doesn't seem representative. If the questions really were unrelated, then the probability of that happening would be 0.35 cubed, which is about 4%. So the teacher might say, look, it's clearly mathematically unlikely that you actually know 65% of the material. However, if there were correlations involved, then even though 35% of all possible quizzes might have you getting that first question wrong, the proportion of those quizzes where you get the second wrong might be much higher than 35%. And the proportion of those where you get the third wrong might be higher still. So the claim that you really know 65% of the material, but just got a 0 due to a statistical fluke in what the quiz happened to cover, is actually a lot more plausible. And this is a common feature of assuming independence. It makes the math clean, but it gives too little weight to probabilities of more extreme events, at least when the subcomponents really correlate with each other like this. Now this distribution that you get when you do assume independence, it has a name. It's called the binomial distribution. It comes up a fair amount in probability, so let's take a moment to generalize it, and to build up to an actual formula to think about. It applies to situations where you have multiple binary events, which means each one can go one of 2 ways, like our quiz questions, where for each question you either get it right or you get it wrong. As an example where it's a little more conceivable that events are independent, maybe think of having n children, each of whom is either a boy or a girl. Just as we've been pondering the probabilities for various scores on the quiz, the distribution is meant to give probabilities that a given number of those n events go a certain direction. For example, what's the probability that exactly 6 out of 10 children are girls? Along with independence, another assumption that this distribution rests on is that the probabilities for each event is the same. For example, a human baby has about a 49% chance of being a girl, and we assume that that value stays constant for all of these children. Under those assumptions, let's do a little math and think through the probabilities. What are the chances that exactly 6 out of the 10 children will be girls? Well, the first step here is to count how many patterns of boys and girls include exactly 6 girls. This is what we talked about in the first video. It's exactly the kind of counting problem that the function n choose k is meant to answer. In this case, what we want is 10 choose 6, which works out to be 210. That is, out of all 2 to the 10 possible gender distributions of 10 children, 210 of them include exactly 6 girls. Because of the independence assumption, the probability for getting any one of these arrangements factors as 10 separate probabilities, each of which is just either 0.49 or 0.51. Moreover, every one of those patterns has exactly 6 0.49s and exactly 4 0.51s, one for each boy. So the total probability of getting 6 girls is 10 choose 6 times 0.49 to the 6th times 0.51 to the 4th. More generally, and for identical reasoning, the probability of getting exactly k girls would be 10 choose k times 0.49 to the k times 0.51 to the 10 minus k. The chances of 3 girls, for example, is 10 choose 3 for the number of patterns that include 3 girls, times the probability for any one of those patterns. As you might recall from Chapter 1, the values of 10 choose k also show up as the 10th row of Pascal's triangle. So the center bulge in our distribution is reflected by the larger numbers in the middle of that row. The sheer number of patterns including 5 girls is just way more than the number including, say, 2 girls. And this is what accounts for the concentration of probabilities near that middle. And of course, you could replace 10 with any other number n. And likewise, for modeling something other than gender, this value 0.49 could be replaced with any other probability, p, which would mean that 0.51 would be replaced with 1 minus p. Shifting that value of p around, it's kind of fun to see how the weight of the distribution moves. Considering just how complicated the probabilities of multiple events joined together can be, this formula, though mildly complicated at first glance, is actually pleasingly simple, and it's a simplicity born from the independence assumption. And again, when the underlying effects do correlate with each other, we can go a little farther than just saying that the binomial distribution will be wrong. If the outcomes of one of your binary events, like answering a single question correctly, actually suggests that the other events are more likely to flip in that same direction, the binomial distribution is going to give too little weight to the high and low ends of the spectrum, and too much weight to the middle. But that's just a heuristic. You might be wondering right now how to find a more precise alternative in the case of correlated events. Is the only alternative really laying out all 2 to the n possibilities broken up into these appropriate conditionals? Well, to start, there usually are some softer simplifying assumptions that you can make that are valid. For example, with the quiz, the order of questions probably doesn't matter, and that really helps collapse down the 2 to the n situations into only a handful of distinct cases, in pretty much the same way that the independence assumption does. But to get more sophisticated from here, what you'd want is a more precise and more mathematical notion of what we mean by correlation, and that's something that you and I are going to cover in a later video. For this video, if there's just one thing that I want you to take away, it's not the formula for the binomial distribution, which is easy enough to rediscover. Instead, it's this sensation of having a setup which is fully accurate but completely intractable on the one hand, and having one that's simpler but known to be inaccurate on the other. The art of math here is a combination of finding the right middle ground between these two, and also just understanding the limitations of conclusions that you do come to. And the more tools you have in your belt, the better equipped you are to do that. But you can see just how tempting it is to apply the binomial distribution a little beyond its scope of accuracy. And given that, when you see it come up in practice, which it does all the time, ask yourself what the underlying independence assumption is, and if it's valid. And the thing is, this assumption is often a lot more sneaky and subtle, because several other distributions that we'll see, like the Poisson distribution or the Gaussian, derive from the binomial, or at the very least from independence assumptions of their own. So the same thoughtfulness and caution is warranted when those distributions come up as well, and the tendency to underweight the probabilities of extreme cases applies much more broadly than just the binomial.